Hi guys, welcome back to our class on electrical and electronic measurements. So today we'll be discussing about a new method for measuring voltages and currents. So this is using a new instrument which is known as the potential transformer and the potential and the current transformer. Potential transformer, which is also known as the PT, and current transformer. Okay, so I hope you guys are very much familiar with what is a transformer, right? To see how a transformer works, we can just simply draw a simple diagram over here. So let's look how the transformer works first. So this is a simple transformer which is a primary and a secondary coil. So this is the primary coil which I'm drawing right now, and let's say we're talking mainly about alternating currents, measuring high value alternating currents. So we have let's say we connect a voltmeter over here, we have a source over here, and let's first look at what are the equations that are associated with these transformers. Now here, what is the voltage ratio of the secondary and the primary? So V1 by V2 will be equal to, it will depend upon the number of turns of the primary and the secondary. So N1, N2. So V1 by V2 will be equal to N1 by N2. We all know these expressions. I think we have studied it in 12th grade as well as in your basic electrical course. So V1 by V2 is equal to N1 by N2 is the turns ratio or the voltage transformation ratio. And if you look at what is the current ratio, I1 by I2 is equal to N2 by N1, not N1 by N2, it is N2 by N1. Now here, what remains constant is the power. The power will always remains. Power is always constant. So let's say if you have more number of turns in the secondary, what happens? The voltage will increase in the secondary because V2 is equal to V1 into let's say we have more number of turns on the secondary, then let's write what is the expression for V2. V2 will be equal to V1 into N2 by N1, which means that since a number of turns in N2 is more than N1, in comparison V2 will be more. You can step up the voltage using this transformer. And let's say in that case, what happens with I2? I2 will be equal to I1 into N1 by N2, which means that I1, the current gets stepped down. So if you multiply V2 and I2, V2 into I2, I2 is the power, P is equal to V2 into I2 of the secondary. Let me just rewrite it. Yeah, V2 into I2, which is the power and the secondary, will be equal to, we can substitute these values, V1 into N2 by N1 into I1 into N1 by N2. So here N1, N2 gets cancelled. You get it as V1 I1. So which is V1 I1 is also the power of the primary coil, isn't it? So you get that the power is always same. The secondary power is V2 I2, which is always equal to V1 I1. Only thing is that if the current gets stepped up, the voltage will get stepped down. If the voltage gets stepped up, the current will get stepped down. So it's a constant power device. So that is how a transformer works. Now, why are we looking at this transformer? Let's say you want to measure a voltage, a very high voltage. You want to measure a very high voltage, alternating voltage, of let's say 1 kilovolt, right? And let's say you have a voltmeter, you have a voltmeter that can measure up to 1 volt. Now there are two ways in which you can do this. You can either connect a series resistance, or what you can do is that you can use a potential transformer. And by using a potential transformer, it is much more easier. We'll look at the reasons why we will be going for the potential transformer. First, let's see how we can do the connections. So here what we do is that we'll take the source, 1 kilovolt source, and let's say you have this, you connect a transformer, connected to a transformer. So this is our source, 1 kilovolt, and from here you connect a small transformer, and I'll connect it to this voltmeter. What we do is that we'll keep the turns ratio as 1000:1. Now when you keep 1000:1, let's call this as V1 and let's call this as V2. The voltage V2 will be equal to, this is N1, this is N2, will be equal to V1 into N2 by N1. Now V1 is 1 kilovolt, as we know, 1K into 1 by 1000, which is equal to 1 volt. So V2, the voltage over here, would be equal to 1 volt in this case. Is it clear? So this is how you can measure high voltage using a potential transformer. Now this can also be done using a by connecting a series resistance. Let's say you have a voltage source of 1 kilovolt and you connect it with a series resistance and a voltmeter. So let's say this voltmeter has a resistance of 1 kilo ohms. Generally voltmeters have high resistances, so let's take this as 1 kilo ohm. So if you want to connect a series resistance, this is 1 kilovolt, this is 1 kilo ohms, and if you want to extend the range, so here this can only measure up to 1 volt, right? So this is basically how much? 1 volt, and this should be ideally take up all the other 999 volt, isn't it? This is the series resistance. So what would be the value of the series resistance? Now if 1 volt is the measurable voltage and 1 kilo ohm is the resistance, what would be the current through this voltmeter? That is the first thing we can look at. So the current I through the voltmeter would be 1 volt divided by 1 kilo ohm, that is 10 raised to minus 3 amperes. So similarly you need 999 volt over Rs. So the resistance Rs would be V by I. Same current 10 raised to minus 3 will flow through the Rs as well. So that's the maximum current. So the resistance would be V by the same voltage current through the voltmeter, and therefore that is 999 divided by 10 to the power minus 3, which makes it 999 kilo ohms, right? So you'll have to connect a 999K resistor in series with this voltmeter in order to measure this voltage in order to extend the range. But the problem here is that when you connect such a resistance and when you use a potential transformer, let's see what is the difference in the values of power consumption, right? So here if you want to find what is the power consumption in the potential transformer, what we'll do is that we'll find what is the power that is consumed in the primary coil of this transformer, right? So the voltage in the primary coil, or let's look at what is the power that is consumed in the secondary coil. Now we know the power in the voltage in the secondary coil is 1 volt, and the current in the secondary coil is 1 divided by 1K, and the resistance is 1K. So P can be written as P is equal to V square by R. So in the secondary, if you look at what is the power consumption, 1 volt is the voltage that is developed, 1 square by 1K, which is 10 to the power minus 3 watts. Considering this transformer is ideal, there is no loss, and generally transformers has very high efficiencies in the range of more than 98-99% efficiencies. So we can neglect the loss in the transformer. Considering this is an ideal transformer, you'll get the maximum power loss or the power consumption by the voltmeter or the current power potential transformer is 10 to the power minus 3 watts. Now at the same time, if you look at what is the power consumption in this setup, here in this series resistance setup, here we can see that the power can be written as P is equal to V square by R. So V is 1000 square, 1000 volt, 1K, by R is 999K plus 1K, which is 1000K, that is 10 raised to 6 by 10 raised to 6, which is 1 watt. So if you look at the ranges here, over here, for the potential transformer it is 0.001 watt, and the power consumption over here is 1 watt, which is a huge difference in comparison. This is only 1 by 1000 of the actual power loss in the series circuit, which means that this potential transformer is much more efficient, which less power it can measure these quantities. Similarly, we'll look at we'll do a small analysis of a current transformer as well. So let's say in a current transformer, we want to measure some current, let's say a current of 1 kilo amperes. Now ammeters generally come in a very small range, and let's say you have an ammeter, the ammeter of 1 ampere, right? Now if you want to measure this, you can use a current transformer, and what you can do is that so 1 kilo amperes is passing through this, and we connect it to a current transformer, and we take the secondary out, and we connect it to a meter. Now here N2, let's take it as the ratio, the number of turns ratio as 1:1000, which means that N1 is to N2 is equal to 1/1000. So this is taken in order to match this 1 ampere with the 1 kilo amperes. So here you can see I1 N1 is equal to I2 N2 is the turns ratio. So I2 will be equal to, I2 is the current in the secondary, will be equal to I1 into N1 by N2. I1 N1 by N2, that is equal to I1 is 1000 amperes into N1 is 1 by 1000, which makes it 1 amperes. So here we obtain the current in the range of 1 amperes, and you can measure the corresponding 1 kilo amperes using a 1 ampere ammeter. Now let's also look at what is the power loss. So here power loss in the sense, like if we connect a meter with a parallel shunt resistance. So let's say we have the alternate method for having a current transformer is that you can have a, which we have already studied, which can have a meter with a shunt resistance, and let's say the ammeter has a resistance of 99.9 ohms, so that 1 ampere current flows through this. So if that is the case, and we want 999 amperes through the shunt resistance RSH, so here what would be the resistance value, what should be the value that should be set in order to get 999 amperes? We can take the current division rule, right? So here 1 kilo amperes is coming up, so 1 ampere which is flowing through the ammeter is equal to the total current, which is 1000, into opposite branch resistance, which is RSH, by 99.9 by the total resistance 99.9 ohms plus RSH. So that would turn out as 99.9 plus RSH is equal to 1000 RSH, which implies 99.9 is equal to 999 RSH. I'm taking the RSH to the left hand side, so RSH is equal to 99.9 by 999. If you cancel these two, you will get it as 0.1. So RSH is 0.1 ohms for this particular scenario, and let's see what would be the power consumed over here. So the power consumed can be written as the voltage P is equal to V into I. Now the voltage over here is 1 ampere. These are parallel circuits, so since these are parallel circuits, the voltage across any of the branch would be sufficient. So the voltage would be in this case would be let's take the voltage across the ammeter, which is 99.9 into 1 ampere. The resistance into current is the voltage, and the current that is flowing through this ammeter over here is, through the entire setup is 1 kilo amperes, which makes it the power consumption in this circuit is 99.9 kilowatts, which is very huge. Now let's look at what would be the power consumption in the current transformer. So here in the current transformer, the resistance of the ammeter is, let's say, the same value, 99.9 ohms, and the current that is flowing through this ammeter is going to be 1 ampere, right? So considering the transformer is ideal, this is ideal transformer, we just have to find what is the power consumed over here in the secondary part. So so the current power loss, the power consumed in the CT is equal to, we can take the formula as the same formula you can use, which is V into I. So the voltage is 99.9 into 1 amperes across the ammeter. The current is 1 amperes, which makes it 99.9 watt, which is the power consumed in CT. But at the same time, the power consumed in for measuring using a ammeter and a shunt resistance is 99.9 kilowatt. So in comparison of these both of these quantities, the usage of CT is much more efficient because we lose less power in this case. Now if we look at what are the other advantages in this case, is that there are a lot of advantages in this case. So main advantage is that you have a 1 kilo ampere source going over here, and current transformer, let's say. So since these two since the primary and secondary are not at all in electrical connection, there is a huge amount of safety over here while placing the ammeter or any other devices over here. So, or if you want to change the range of the ammeter, or want to place a different ammeter or anything, you don't have to touch the primary circuit. The primary circuit can continue with its functioning. You don't have to disconnect the circuit or anything of that sort in this primary circuit. You can do everything from over here, and since you can use a switch over here and do everything from here, which is very easy. As well as the second thing is that since we are using a transformer, there is always a electrical isolation. There is a electrical isolation which brings huge safety to the users, because it is magnetically transferred to this part, and therefore if you off the switch, there won't be any other problems in the secondary. So that is a huge advantage of having a CT and you can measure the currents of any live wires using such a connection without even affecting the live wire. That is one of the main advantage. Second is that you can easily change the range, range of operation, range of currents or anything. And the other thing is that very is less power consumption in comparison. Very less power consumption. You can easily insert or replace meters or anything you can do. You can also use this for these circuits are generally used for relays and circuit breakers and all those things, because for protection purposes. So you can always sense the current at any point of in your circuit, and then correspondingly if the currents increase or decrease, you can directly on the of the circuit by using a circuit breaker and a relay. So these are the main advantages of CT, and the same goes with PT as well, because in PT also there is a transformer, and because of which you don't have to you don't have to get in contact with the primary circuit. You can let the primary circuit work on its own, and you can do all the work on the secondary circuit. You can sense the current and the voltage and everything, and that is a much advantages in comparison to the general connections of the voltmeter. If you have to connect a voltmeter to this to a circuit, it is a bit more difficult connecting it to the primary of the circuit, but then since you have a electrical isolation using this transformer, it would be much more easier. I hope this is clear. Okay guys, we'll wind up over here. Yeah.